welcome to the last session of this course, and we were looking into the chemical process enhanced separation in a batch dialysis process. We have written down, we have taken an example of aniline separation from the feed using sulfuric acid in the dialysate side, and we have seen that how the aniline reacts with sulfuric acid, forming the anilinium ion, maintaining the 0 concentration of aniline in the dialysate side. So, thereby we can maintaining the maximum concentration gradient or driving force, so that we can have the maximum separation possible. So, we have written down the governing equation of the solute 1 in the feed side, we have written down the governing equation of the solute 1 in the dialysate side, and now we will look into the initial condition of this problem. The initial conditions are: at time t is equal to 0, we have C1f is equal to C1f naught and C1d is equal to 0, because there is no solute initially, and C3d equal to 0, because there is no anilinium ion also formed initially. Now, C3d can be obtained by the equilibrium relationship, because it is equilibrium governed reaction. So, it is K equilibrium is equal to C3d divided by C1d times C2d, where C2d is constant, because this sulfuric acid, 2 is the sulfuric acid, and this is constant because it is in excess. 2 is in excess. Okay. Now, we take the Laplace transform and of both the equations like before, and see what we get. So, from the first equation we will be getting K by Vf Cid bar, these are transform variables. Cif bar is equal to S C1f bar minus C1f naught, and from the second equation we get K by Vd C1f bar minus C1d bar is equal to S C1d bar minus C1f naught plus S C3d bar minus C3d 0, which will be basically 0 at time t equal to 0. So, from these two equations, what is resulted is that we can write down K by Vf C1d bar is equal to K by Vf plus S 1 plus Vd over K 1 plus C2d, C2d is a constant, times S C1d bar minus C1f naught. Okay. And by simplifying, we can get C1d, expression of C1d bar is equal to C1f 0 divided by As plus Bs square, where A is equal to Vd by Vf 1 plus C2d, and B is equal to Vd by K 1 plus C2d, and we can take a inverse Laplace and can obtain C1d as a function of time. So, this is straightforward. We can really do that and can get the profile of concentration of aniline in the dialysate side and how it varies as a function of time. So, this is the modeling of a batch cell, which is where the dialysis is separation of dialysis enhanced by an external chemical reagent. So, this must also be known to a student, that how we can maximize the driving force during a dialysis process and how to model the situation. Next, we will be going a detailed 2-dimensional analysis in an actual dialysis operation for a continuous steady state system. So, we will be doing a detailed 2-dimensional analysis of dialysis process. So, let us say this is the feed side. Okay. the feed is flowing as a laminar flow, laminar parabolic profile. So, this is feed going into the system in the feed side, and will be setting up our x axis in the middle of the channel, this y in this direction. So, this is y equal to h, this is y equal to 0, and we have placed a membrane here, dialysis membrane there, and this is the dialyzed side. So, there is a feed side, this is a dialyzed side, and this is the dialyzed side as well, both side, and it will be having a concentration profile something like this in the middle. So, now, so it's basically the feed is like this. This is a parabolic velocity profile. So, if we consider a Newtonian fluid laminar and one dimensional flow, the velocity profile as we already know it's a parabolic velocity profile 1 minus y square over h square. So, y is the midplane of the channel, in fact, this is fixed here, is y equal to 0. Okay. Y is the midplane of the channel and h is the half height. Next, we write down the Q. Q is equal to 2 volumetric flow rate 2 U0 WH. Okay, this is the volumetric flow rate. Okay. So, we are assuming that the channel is quite wide compared to the channel height. Okay. W is much greater than 2h. So, that is the assumption. Now, at the steady state, we write down the solute balance within the channel. Solute balance in the channel, that means the channel is ranging from minus h to h is the half height, minus h to plus h, and we write down the governing equation u del c del x is equal to d del square c del y square. So, now this is an ideal dialysis process where the concentration gradient, the only driving force that is appearing in the system is the concentration gradient, and unlike the earlier cases, the pressure driven membrane based processes, we did not have any pressure gradient, pressure operating into the system. So, therefore, there is no convective flux in the y direction. We will be having the solute flux in the x direction only. So, at x so there is no v del c del y term is present in this equation. So, at x equal to 0, we have c is equal to c naught, and at symmetry in the midplane at y is equal to 0, we have del c del y will be equal to 0, and at y is equal to h, we have molar flux minus d del c del y should be equal to p times c, where p is the membrane permeability. Membrane permeability towards the solute. So, therefore, we are assuming that the dialysate site concentration is extremely dilute. CD is very dilute and can be considered to be 0 at any point of time. So, this system is a typical eigenvalue problem, and let us make it non-dimensional and see how it how the solution can be obtained. So, C star we defined as C by C naught, Y star we define as y over h, x star we defined as x d divided by u0 h square, and p star is membrane Biot number they called it. So, this will be pH over d, and this is also known as the membrane Biot number. So, let us look into the governing equation and the boundary conditions in the non-dimensional version. So, 3 by 2 1 minus y star square del c star del x star is equal to del square c star del y star square. This is the governing equation. The boundary conditions become at x star equal to 0, my c star is equal to 1, at y star is equal to 0, del c star del y star equal to 0, and at y star is equal to 1, we have del c star del y star plus p star c star equal to 0. Now, this equation is we can able to solve this equation by using separation of variable, and all of you must be knowing the separation of variable, and the analytical solution can be obtained. The analytical solution will be in the form of c star as a function of x star y star will be summation, it will be represented in the summation series m is equal to 1 to infinity a m exponential minus 2 by 3 lambda m square x star and summation of a m n y star, where the n runs from 0 to infinity. So, the eigenvalues of the systems. So, this is a standard eigenvalue problem, and the eigenvalue. So, this is a standard eigenvalue problem or Sturm-Liouville problem. So, eigenvalues of the systems are lambda m. Lambda m's are the eigenvalues of the system, and then we will see how the solution will evolve. So, once if that is the case, then rate of removal of the solute can be written as let us say this is the mass per unit time, that will be in kg per second. Let us say this is in kg per second. We removed will be 2 u0 h times w. W is the width, channel width, multiplied the C0 minus CCM. What is CCM? CCM is the cup mixing concentration across the channel. So, it is some kind of average concentration. Of solute in the channel. Okay. So, C naught is the fit concentration, h is the half height, 2h is the total height, u0 is the velocity, w is the width. So, we can now next we will be finding out what is the cup mixing concentration. Cup mixing concentration is given as by this expression. It is some kind of cross sectional average concentration 0 to h 3 by 2 u naught 1 minus y square by h square dy, and this will be 0 to h 3 by 2 u naught 1 minus y square by h square c as a function of x and y dy. So, this expression can be integrated quite easily, there is absolutely no problem in that. we have already found out what is the expression of C as a function of x and y, that can be integrated across the y. So, the x variation will be intact. So, I will be getting ultimately CCM as a function of concentration. So, how the cup mixing concentration or the average concentration in the feed side will be varying along the x, that expression can be obtained by this. So, if you look into the expression of that non-dimensional version of that, CCM star is equal to nothing but CCM divided by C naught, and this will be, after integration we will be getting this expression summation of m is equal to 1 to infinity am exponential minus 2 by 3 lambda m square x star summation of n equal to 0 to infinity a n m divided by n plus 1 into n plus 3. Here the eigenvalues are the roots of the polynomial. Lambda m are roots of polynomial of the form 0 equal to p star minus 2 by 3 plus 5 by 12 p star lambda m square plus 1 by 20 plus 1 by 45 p star lambda m to the power 4. So, this will be the polynomial that the roots are the eigenvalues. So, what is A0 m? A0 m is equal to 1, A1 m is equal to 0. So, basically the event terms will survive of the series minus lambda m square by 2 and A3 m is equal to 0. Likewise, A4 m will be equal to lambda m square 2 plus lambda m square divided by 24. A5 m is equal to 0. Likewise, it will go, and capital AM will be given as summation of n equal to 0 to infinity A n m divided by n plus 1 into n plus 3, and there will be double summation in the denominator n equal to 0 to infinity p is equal to 0 to n, and this will be a p m a n minus p times m divided by n plus 1 into n plus 3. Okay. So, now let us do a certain simplification. Simplification is that, as we can see that the solution has a x dependence in form of exponential minus lambda m square x star. So, lambda m will be large value and its square will be large. So, therefore, exponential decay will be faster. So, if we take care of that, and we consider the, since the exponential decay is faster, we can take the first term as the first eigenvalue. Decay is fast, and we can consider the first eigenvalue. That will be lambda 1 square is equal to p star divided by 2 by 3 plus 5 by 12 p star, and consider the first term of series. If you do that, then a typical then plot log CCM star versus p star x star, and we will be getting a performance curve. We compute taking the first eigenvalue, and the performance curve will be looking something like this. We will be having log CCM star here, and p star x star will be nothing but p x by U0H, and the curves will be like this for different value of P star. This for P star is equal to 1, this for P star is equal to 0.1, this for P star equal to 0. That means there is no permeation of the solute to the membrane, it is impermeable. So now if you talk about the if you would like to design what is the length of the dialyzer length for a particular removal of the solute, then we can from that particular removal solute we can estimate the value of CCM star. We can directly go for that value of P star. If P star is 0.1, we can directly come here and get the value of X star. So we know this coordinate system. So P is known to us, U0 is known to us, channel height is known to us. So we can get the value of X. So likewise, for different value of for different types of membrane where the P star will be known, we can get the curve for a let us say 99% separation, 98% separation of a solute from the feed side. So we can get the length of the dialyzer. If the length of the dialyzer is known, then from here one can find out what will be the h of the height of the dialyzer. So if the P star is not known, so we can then we have to interpolate between the two known values and can find out the design of the dialyzer, can find out the length of the dialyzer or the height of the dialyzer. If one of them is fixed, then other can be evaluated. So thus in a continuous system, for a two-dimensional model, which will be a basically and a very realistic model can be obtained, can be utilized to design a dialysis. Next, what we will be looking? We will be looking into a very simplified version of this model, which so that the analytical solution will be in front of us. So let us look into a simplistic approach. First, we consider the feed velocity is large. And we will be having a plug flow. Dialysate is dilute. And third, it is a steady state operation. So if it is a plug flow, or we will be having a uniform velocity profile, u is equal to u naught, then our whole analysis becomes simplified, and we will be having u0 del c del x is equal to d del square c del x square. Okay. And take the non-dimensional version, c star is equal to c by c naught, y star is equal to y by h, and x star is equal to x by L. So if that is the case, it becomes a del c star del x star is equal to del square c star del y star square. So now this equation is easy to solve, and there will be a analytical solution is obtained here. So a is equal to u0 h square by dl. This can be written as 1 by 4 Reynolds Smith d by L, as we have done earlier. The non-dimensional version of the governing the boundary conditions will be, you can write directly that at y star is equal to 0, my del c star del y star will be equal to 0, and y star is equal to 1. We have del c star del y star plus Pm c star is equal to 0. So what is Pm star? Pm star is nothing but pH over d. D is the diffusivity of solute through the membrane matrix, and at x star equal to 0, we have c star equal to 1. Now we can use a separation of variable type of solution, and we can have a we can assume the concentration can be a function of sole function of x and sole function of y, and if you really do that and put into the governing equation, this will become a by x dx dx star is equal to 1 over y d square y dy star square. The left hand side is a function of x alone, the right hand side is a function of y alone. They will be equal, and they will be equal to some constant. Let us say this constant is minus lambda n square. So, the solution is x is equal to C1 exponential minus lambda n square x star by a, and the y varying part is d square y d y star square plus lambda n square y will be equal to 0, and we will be having the boundary condition that at y star equal to 0 dy star equal to 0 and y star is equal to 1, we will be having dy star plus p m y is equal to 0. So, this will be having a solution y is equal to some c c n cos lambda n y star, and the eigenvalues will be nothing but the roots of the transcendental equation of lambda n tan lambda n is equal to p m. So, from this transcendental equation, roots of these equations will be the eigenvalues, and one can get the final solution as x star y star is summation of all these solutions. So, this becomes C n cosine lambda n y star exponential minus lambda n square x star by a. Okay. So, from by using the boundary condition, initial condition that at x star equal to 0, c star is equal to 1, we can get the value of C n by using the orthogonal properties of the sine and cosine functions. So, if we really do that, the C n will become 0 to 1 cos lambda n y star dy star divided by cos square lambda n y star dy star, and one can really do a calculation of the, you can evaluate the integrals, and this becomes that C n becomes 2 sin lambda n divided by lambda n p m square plus lambda n square divided by p n square plus p m plus lambda n square, and ultimately we can get the expression of c star as a function of x star and y star is equal to summation of C n cosine lambda n y star exponential minus lambda n square x star divided by a, n equal to 1 to infinity, and then we can evaluate the cup mixing concentration, and by definition, as we have done earlier, the cup mixing concentration in this case will be, we carry out the integration, and let's write down the expression first. V x y, so it is uniform here u 0 c x y dy from 0 to 1, here it will be 0 to 1 u 0 dy. So, you will be getting the expression of cup mixing concentration as C n exponential minus lambda n square x star by a times sin lambda n divided by lambda n. That will be the expression of CCM star, and mass removed is rate of removal of pollutant will be 2 u 0 h times w C naught minus CCM. Then this can be, after multiplying by C naught, if you can put this expression, one can get the rate of removal of the pollutant through the dialysis process. So, this is how the dialysis process can be modeled either by one dimensional model or detailed 2 dimensional model we have discussed, and I hope now we have really come down to the end of our course. So, let us summarize whatever we have learned in this course. In this course, we have learned the basic principles and the various membrane based fundamentals of various membrane based processes, their underlying transport mechanisms. Then we have categorized various processes in terms of reverse osmosis, nanofiltration, microfiltration, ultrafiltration, and then membrane modules. We have discussed membrane modules as well as the dialysis process. We have looked into the various important terms and definitions. Those were required tremendously for modeling the systems. We have looked into the how from irreversible thermodynamics the transport laws in case of reverse osmosis through the porous membrane can be obtained. Then we have looked into the fouling, reversible and irreversible fouling, and as well as the concentration polarization. Then we have looked into the one dimensional analysis of concentration profile, concentration polarization, and summarized the shortcoming of one dimensional model, and looked into the osmotic detailed two dimensional model for the osmotic pressure control filtrations. We have looked into details of the osmotic pressure control filtration for dilute solution, for concentrated solution, for developing for one dimensional model, two dimensional model, things like that. And then we moved into the gel layer polarization filtration system, and we have looked into the detailed modeling of gel layer contouring filtration. After that, then went forward to the membrane modules and how to covered how to do the modeling and how to formulate the design equations to model the membrane module and how to obtain the solutions as well. And again, in this case as well, we have gone into step by step complicated step. Initially, at the very first instance, we considered the very simplistic case for constant permeate flux. Then we have taken the complexity to a second level where the permeate flux is proportional to the delta P or the pressure gradient, and then we got the solution. Then we went into the next step, that is the most complicated step, where it is proportional to delta P minus delta pi, where the osmotic pressure is not negligible at all. We have solved that case. Then we have gone into the dialysis process and looked into the design equations for the batch dialysis, continuous dialysis, then batch dialysis with enhanced chemical reaction, enhanced separation, and then finally we have looked into the two-dimensional model of a continuous dialysis process. I hope you will be getting you have got a fair idea how to model and design the membrane-based separation systems, starting from the pressure-driven processes up to the dialysis operation. And I hope that this course will be of immense help for you to your future research, for your future career in research or in industry. Thank you very much.